Find your space. Whether you are sitting comfortably or lying down, just allow your body to grow heavy. Give yourself permission to let go of the day, to let the weight of your thoughts settle, and then to release them. If it feels right for you, gently close your eyes. Let us begin with a simple breath. Take a deep breath in, filling your lungs with air, feeling your chest expand. Hold it for just a moment. And now a slow, long breath out. Feel the tension leaving your shoulders, your jaw, your hands. Let us take one more just like that. Inhale calm and exhale the noise. We are about to begin a journey. This is not a journey that requires maps or ships, but one that requires only your mind and your willingness to wander. We are setting out on a voyage through the vastness of space and the depth of time, and our journey begins right here. Before we travel to the distant stars, we must first find our anchor. Feel the surface beneath you. Notice the solid support of the chair, the floor or the bed. Acknowledge the room you're in, the solid walls, the ceiling above you. This is your safe harbor. This is your immediate reality. Now let your awareness expand. Feel the presence of the building around you, the street outside the city or town where you live. Feel the curve of the land, the presence of the continent, all resting on the gentle curve of our world. Let your mind begin to float. Gently, softly let it rise upwards. Moving above the roof, climbing past the thin white clouds, moving higher and higher, till the sky fades from blue to the deep velvety black of space. From here, look down, look back at our home. It is not a collection of borders or a list of names. It is a single beautiful sphere of swirling white clouds, deep blue oceans, and patches of brown and green. A marble of impossible beauty hanging in the quiet. This is Earth. From this distance, as the great astronomer Carl Sagan once helped us see, our planet is just a pale blue dot. Imagine that, a tiny speck of light, a single mote of dust suspended in a sunbeam. It is floating in an immense, overwhelming darkness, a vast cosmic ocean. This dot is our oasis. It is fragile and it is profoundly rare. On this tiny point of light is every person you have ever loved, every song ever sung, every idea ever thought, every war ever fought. Everything that makes us human, all our joy, all our sorrow is contained on this precious, vulnerable world. This is our anchor. This is where our story begins. But we are not separate from the great Atlantis that surrounds our dot. We are part of it. We are made from it. This is the true heart of our journey. We often look up at the stars and feel small, we feel distant and separate. But the truth is, the universe is not just out there. It is also in here. It is inside us. The atoms in your left hand, the iron in your blood, the calcium in your bones, these materials were not created here on Earth. They were forged billions of years ago in the fiery hearts of exploding stars long before our sun or our planet even existed. When we look out at the cosmos, we are looking at our own origin story. To understand the universe, to truly grasp the scale of the galaxies and the nature of light, is also to understand ourselves. It is a journey to discover our own place in this grand unfolding story. The Earth whispers its own history, and the stars echo that whisper across eternity. We are the listeners. We are the children of the cosmos, waking up on this small blue dot, trying to remember where we came from. So let your mind rest on this thought. You are a part of this planet, and this planet is a part of the universe. Keep breathing. Let the anchor of Earth hold you as we prepare to look deeper. We pull back from the incomprehensible scale of the galaxies and find a single familiar star. Our star. We are moving now not through the empty void between galaxies, but through our own cosmic neighborhood. Our home, the solar system, and at the very center of this home, holding it all together, is our hearth, our anchor, the sun. It hangs in the blackness, a perfect sphere of blazing light. But it is not a fire, not like a log burning in a fireplace. A fire is chaotic, a chemical reaction. The sun is something far more profound. It is a star. It is a magnificent, stable 4.5 billion-year-old engine. Deep in its core, the pressure is unimaginable. The weight of the entire star is crushing down, creating a heat of 15 million degrees. In this cosmic forge, the sun takes the simplest and most common element in the universe, hydrogen, and performs a miracle. It forces the tiny cores of these hydrogen atoms, the protons, to overcome their natural repulsion and slam together. They fuse. This is nuclear fusion. In this process, 4 hydrogen atoms are crushed into one new atom, helium. But here is the secret: the one helium atom weighs just a tiny, tiny bit less than the 4 hydrogen atoms that made it. Where did that little bit of lost mass go? It wasn't lost, it was converted. It was transformed into a burst of pure energy, an explosion of light. This light, this energy, begins a long journey. It may take 100,000 years just to struggle from the sun's core to its surface. But once it breaks free, it streams out in all directions, travelling at the ultimate speed limit. 8.5 minutes later, that ancient light born from fused atoms crosses 93 million miles of empty space. It warms the face of the earth. It lands on your skin. It feeds the leaves of a tree. It is the energy that powers our world, the energy that powers us. The sun is not an angry god. It is a steady, reliable heart patiently turning matter into life. Let us drift away from this beautiful furnace into the realm it governs. We move first toward the inner worlds. These are the rocky planets, the ones forged from the heavy dust and metal that could survive the sun's early heat. The first world we meet is Mercury. It is a tiny, scorched messenger hugging close to the fire. It has almost no atmosphere to speak of. Its face is covered in craters, a history of ancient impacts. Because it has no blanket of air, its temperatures are extreme. The side facing the sun bakes at over 400 degrees Celsius, hot enough to melt lead. But the side turned away in the long night plunges to a cold of negative 170 degrees. It is a world of fire and ice locked in a tight, fast orbit. We drift outward past the searing heat to the second planet, Venus. From Earth, it is the most beautiful object in our sky, save for the moon. It shines like a brilliant white jewel at dusk or dawn. It is our sister, almost the exact same size as Earth, but this sister took a very different path. If we were to descend through its clouds, we would not find beauty. We would find a hell. The atmosphere of Venus is a thick, crushing blanket of carbon dioxide 90 times heavier than Earth's. This blanket has created a runaway greenhouse effect. It traps all the sun's heat, making the surface of Venus hotter even than Mercury. Its air is filled with sulfuric acid. The pressure would crush a submarine. Venus is a profound lesson in how fragile a paradise can be, a vision of a world that was lost to its own atmosphere. We continue outward, past our own blue-white marble, our home, which we will return to, and we arrive at the fourth stone from the sun, Mars, the red planet. It is half the size of Earth, a world of cold, rusty dust. Its air is thin and cold, but as we drift over its surface, we see things that feel familiar. We see the shadows of giant dormant volcanoes, one of which, Olympus Mons, is 3 times taller than Mount Everest. We see a vast canyon, Valle Marineris, that would stretch all that away across the United States. And most importantly, we see the winding, empty beds of ancient rivers. We see the deltas where these rivers flowed into vast, shallow lakes. Billions of years ago, Mars was not a red desert. It was a blue world. It had water. It had a thicker atmosphere. It had potential. Today it is a silent, sleeping planet. Its water is locked away, frozen in its polar ice caps and buried beneath its ruddy soil. We leave these small rocky worlds of the inner system. We cross a great divide, the asteroid belt, a vast ring of millions of pieces of rock and rubble, the leftover building materials from a planet that never formed. We are now entering the realm of the giants. These worlds are not like Earth or Mars they are not made of rock and metal. They are titans, made almost entirely of the same light gases as the sun, hydrogen and helium. The first we meet is the undisputed king, Jupiter. It is a monster. It is so large that all the other planets in the solar system could fit inside it. It doesn't have a solid surface to stand upon. It is a swirling, churning ocean of gas and clouds. Its surface is just the top of this endless atmosphere striped into beautiful, terrible bands of white, red and brown. These are storms. The entire planet is a storm, and there staring back at us like a baleful eye is the Great Red Spot. It is a hurricane wider than 2 Earths that has been raging for at least as long as we have been able to watch it. Jupiter is so massive it is almost a failed star. Its gravity is a powerful shield protecting the inner planets by catching and flinging away dangerous comets. We drift past this magnificent king and we come to the jewel of the system, Saturn. It is another gas giant, paler, more serene than Jupiter. But it is defined by the most elegant feature in our solar system, its rings. They are not solid. From this distance they look like a smooth, glowing halo. But as we get closer, we see them for what they are, billions upon billions of individual pieces of pure water ice. Some are as small as dust, others as large as a house. Each one is in its own perfect orbit, a glittering, shimmering river of ice wider than a planet, but in many places no thicker than a 2-story building. They are the remnants perhaps of a moon that strayed too close and was torn to shreds by Saturn's gravity. They are a silent, beautiful testament to both creation and destruction. We are far from the sun now. The warmth of the hearth is a distant memory. The sun itself is just the brightest star in a black sky. We float on into the deep, cold and silent dark. We pass the ice giants. Uranus, the strange one, tipped over on its side, rolling through its orbit like a cosmic barrel. And Neptune, the last true planet, a world of deep ethereal blue, home to the fastest, coldest winds in the solar system. Beyond this, we enter the true frontier, the Kuiper Belt. This is the attic of the solar system, a vast, dark, cold region filled with the leftovers from its creation. Billions of icy bodies, comets in waiting, and small frozen worlds. This is the home of Pluto. These are the scattered, frozen remnants from the dawn of our solar system waiting in the darkness, billions of miles from the light. Now I want you to settle in, let your shoulders relax, and just listen. We've been looking out into the vast emptiness, but now let's look in. Let's look at the shape of our own home. On the clearest nights, far from the glare of city lights, you can see it. A faint, milky band of light splashed across the heavens like a delicate brushstroke or a river of spilled starlight. Ancient cultures saw it as a celestial river, a pathway for souls or the spine of the night. We call it the Milky Way. What you are seeing isn't something out there. It's not another object in the distance. You're seeing our own home. That faint, shimmering cloud is the view from inside our galaxy. Because our galaxy, the Milky Way, is shaped like a vast flat disk, a spinning platter of stars, dust and gas. Our tiny solar system is embedded within that disk about 2/3 of the way out from the centre. So when we look up at that Milky Band, we are looking through the densest part of the disk edge on. We are looking into the thickest part of the forest from the inside. It's the combined hazy glow of billions upon billions of stars, all so far away that their individual lights blur together into one luminous fog. It's a profound perspective shift. You're not just on a planet, you're inside a galaxy. That band of light is your city, your neighbourhood seen from your own front yard. Now imagine we could gently lift ourselves up, moving perpendicular to that disk, travelling for thousands of light years. Imagine floating far above it, looking back down. What would we see? We would see one of the most magnificent structures in the cosmos. Our Milky Way is a barred spiral galaxy. It's a breathtaking pinwheel of light, a celestial hurricane frozen in time, spanning over 100,000 light years from one side to the other. At its heart is a bright, dense, glowing bar of older yellowish stars. From the ends of this bar, majestic spiral arms unfurl and wrap around the core. These arms are cosmic traffic jams. They are regions where the density of gas and dust is higher, triggering furious waves of new star formation. This is why the arms are so bright and distinct, glittering with the intense blue-white light of young, massive hot stars. There are 4 major arms and several minor ones. And where are we in this grand swirling city? We are not in the chaotic, crowded centre. We are not on the lonely, dark fringes. We are nestled in a smaller partial arm called the Orion Arm, or sometimes the Orion Spur. It's a quieter branch, a kind of peaceful suburban neighbourhood tucked between 2 of the massive primary arms, the Sagittarius Arm and the Perseus Arm. It's a good place to be, perhaps even a lucky one. Our relatively quiet location has protected our solar system from the intense radiation and gravitational disruptions that are common in the more crowded parts of the galaxy. It has given life on Earth the time, billions of years of relative calm to evolve and to flourish. From our calm vantage point in the Orion Arm, we can look inward toward the heart of the storm. Let's take a journey there now, not with a spaceship, the distance is too great, 26,000 light years, but with our minds. Let your mind drift, letting go of our small blue world, and begin the long fall toward the galactic core. As we leave our quiet neighbourhood, the stars begin to change. The gaps between them shrink. We move past the bright blue nurseries of the spiral arms and into the older, denser regions. The sky is no longer black with pinpricks of light. It is a solid, blazing wall of illumination. We are entering the central bulge. Here the stars are packed 1,000,000 times more densely than they are in our neighbourhood. If we lived on a planet here, there would be no night. The sky would be a blinding tapestry of thousands of suns, many appearing as bright as our own moon. The gravitational pull from these neighbouring stars would be immense, constantly tugging and disrupting any planets. It is a beautiful but violent place. We push deeper toward the very centre, the final point. The stars here are ancient, moving at incredible speed, swarming like bees around an invisible centre. They are orbiting something they cannot escape. We have arrived at the galactic heart. It is not a bright star or a shining throne. It is a point of perfect impossible darkness. This is Sagittarius A star. It is our galaxy's supermassive black hole. This is the anchor, the gravitational engine around which our entire galactic city of 400 billion stars revolves. It is a monster of truly unimaginable proportions containing the mass of more than 4 million of our suns, all crushed into a single point of zero size. It is the gravitational heart that holds our spiral arms in their elegant dance. This brings us to one of the most mysterious and awesome concepts in all of cosmology, the black hole. What is it? To understand a black hole, you first have to understand gravity. We tend to think of gravity as a pull, an invisible rope. But Albert Einstein gave us a new picture. He said that space and time are not separate things, but are woven together into a single four-dimensional fabric called spacetime. Imagine spacetime as a vast flat trampoline. If you place a bowling ball on it, the fabric sags and curves. If you then roll a small marble nearby, it doesn't get pulled by the bowling ball. It simply follows the curve in the fabric that the bowling ball created. That is gravity. Matter tells spacetime how to curve, and spacetime tells matter how to move. Our sun is like a medium-weight ball creating a gentle dimple in the fabric. Our Earth is like a marble rolling around in that dimple held in a stable orbit. Now, imagine you take a star much, much heavier than our sun. When it runs out of fuel, it collapses under its own immense weight. It collapses and collapses and collapses, shrinking smaller and smaller. As it shrinks, the curve it creates in spacetime gets steeper and deeper. It's like taking that bowling ball and squeezing it down to the size of a pebble. The pebble would have the same weight, but it would create a much sharper, deeper pit in the trampoline. A black hole is what happens when you take a massive amount of matter and crush it down to an infinitely small point. This point, called the singularity, creates a curve in spacetime so deep, so steep that it becomes a bottomless pit. It's a warp in the fabric of reality itself. Anything that gets too close a beam of light, a planet, a star, is trapped and must follow that curve down into the center. The edge of this pit, the boundary from which nothing can escape, is called the event horizon. It is not a physical surface, it is simply the point of no return. Once you cross it, all paths, all possible futures lead to the center. Even light, the fastest thing in the universe, cannot climb back out, and so the object appears perfectly black. There are two main types of these cosmic wonders. The first kind are called stellar mass black holes. These are the ghosts. They are the collapsed remnants of individual giant stars that were perhaps 20 or 30 times more massive than our sun. When these giants die, they don't fade away. They explode in a cataclysmic blast. But their hearts, their cores collapse inward, punching a hole in space-time. Our galaxy is littered with these stellar ghosts, perhaps 100 million of them silently drifting through the darkness. But Sagittarius A star is something else entirely. It belongs to the second kind, the supermassive black holes. These are the anchors. They are not the ghosts of a single star, they are the primordial monsters with masses millions or even billions of times that of our sun. We find them in the centers of almost every large galaxy we look at, including our own. How did they get so big? Did they start small and just eat? Did they grow by swallowing gas dust and countless stars over billions of years? Or were they born this way, formed from the direct collapse of colossal clouds of gas in the early universe? We don't fully know. They are the great dark mysteries sitting at the heart of every island of light in the cosmos. And yet this galactic center, this place of chaos and gravity, is connected to us. The story of the galaxy is not just the story of its endpoints like black holes, it's the story of its cycle. The galaxy is not a static museum. It is a living, breathing ecosystem. It is a place of constant birth, life and death, and this cycle is responsible for your existence. Let's go back to the spiral arms, those bright misty regions we saw from above. Those aren't just pretty clouds, they are stellar nurseries. We call them nebulae. They are unfathomably vast clouds of cold interstellar gas, mostly hydrogen and tiny grains of dust. They drift in the darkness for eons, but slowly, gently, gravity begins to pull them together. A shockwave from a distant exploding star might pass through, or two clouds might gently collide, giving gravity the nudge it needs. Tiny clumps of gas and dust begin to form. They attract more gas and dust. They grow denser. As a clump grows, the pressure and temperature at its core begin to skyrocket. It grows tighter and tighter, hotter and hotter, until at 10 million degrees a new fire is lit. A process called nuclear fusion ignites. Hydrogen atoms are forced together to create helium. In that moment, a tremendous burst of energy is released. The core switches on. A star is born. This new star, a newborn sun, blows away the remaining gas and dust around it, and its new light shines out, illuminating the very nebula that gave it life. This is how our sun was born 4.5 billion years ago in a long-faded stellar nursery. But the story does not end with birth. For a star to create us, it must first die. Stars like our sun, which are relatively small, will live for 10 billion years. When they run out of hydrogen fuel, they will swell up, puff off their outer layers, and then fade into a small dense ember called a white dwarf. A quiet death. But the giant stars, the blue-white behemoths, 10, 20 or 50 times the mass of our sun, live fast and die young. They burn through their fuel in only a few million years, and when they die, they do not go quietly. When a massive star exhausts its fuel, the fusion in its core stops. The outward pressure that was holding the star up suddenly vanishes. Gravity wins instantly and catastrophically. The star's outer layers, weighing octillions of tons, collapse inward at 1/4 of the speed of light. They slam into the star's dense, unyielding core and rebound in the single most violent event in the universe, a supernova. The star explodes. In one blinding flash, it can outshine its entire galaxy of billions of stars. The explosion sends a shockwave racing through space, scattering the star's contents across thousands of light years. But this is not just an act of destruction. It is the ultimate act of creation. You see, the universe was born with only the simplest elements, hydrogen, helium, and a tiny bit of lithium. Everything else, all the elements that make up our world and our bodies, had to be made. The factories that make them are the cause of these massive stars. As they burn, they fuse simple elements into more complex ones. They create carbon, nitrogen, and oxygen. In their final dying moments, the unimaginable heat and pressure of the supernova explosion itself creates the heaviest elements, gold, silver, platinum, uranium. And then the explosion scatters these new precious elements across the galaxy. They mix with the cold hydrogen clouds, the nebulae. These newly enriched clouds then collapse to form the next generation of stars, and critically the planets that orbit them. Look at your hand. The iron in your blood, which carries oxygen to your brain, was forged in the heart of a massive star that died billions of years ago. The calcium in your bones, the carbon in your DNA, the oxygen you are breathing right now, all of it was created in a stellar forge and scattered by a supernova. You are not just living in the universe is living in you. Every atom of your body, except for the ancient hydrogen, was once inside a star. You are quite literally made of stardust. We are the children of the stars. We are the galaxy's way of becoming conscious of itself. And as you drift, as you feel the slow, steady rhythm of your breathing, just rest in that knowledge. You are part of this grand cosmic cycle. A cycle of death and rebirth, of dust becoming stars and stars becoming life. For all of human history, the universe was the Milky Way. Our galaxy, a shimmering river of stars splashed across the night sky, contained everything we could see, every star, every constellation, every faint cloud or nebula. We believed we lived in a single vast island of light surrounded by an infinite empty ocean. The leap beyond our galaxy was perhaps the single greatest expansion of human perspective. It was not a physical journey, but a mental one. It began with a great debate in the early 20th century. Astronomers argued over faint fuzzy patches of light like the one in the constellation Andromeda. Were these spiral nebulae just clouds of gas inside our own Milky Way, perhaps new solar systems being born? Or were they something truly radical, entire island universes just like our own, but located at distances so vast they defied imagination? The question was settled in the 1920s by the astronomer Edwin Hubble. He used a new giant telescope to look at the Andromeda Nebula. Inside it, he found a special kind of star, a Cepheid variable. These stars are cosmic lighthouses. They pulse in brightness, and the speed of their pulse is directly linked to their true brightness. Imagine you see two lighthouses. One is pulsing slowly, and you know all slow pulsing lighthouses are as bright as a spotlight. The other is pulsing quickly, and you know all fast pulsing ones are only as bright as a candle. By measuring their pulse, you know their true power. Hubble measured the pulse of a star in Andromeda. He calculated its true brightness, and then compared it to how dim it looked from Earth. The result was staggering. To be that dim, the star and the entire Andromeda Nebula it lived in had to be millions of light years away. It was not inside our galaxy. It was a completely separate massive galaxy, an island universe all on its own. In that moment, the universe grew from one island to billions. The leap was complete. We were no longer the center of everything, but a single member of a vast cosmic archipelago. The great dark ocean between the stars was not empty. It was intergalactic space, and it was crossed by the light of countless other galaxies, each one a home to billions or trillions of stars. Our closest neighbours, out of all the islands in the archipelago, one stands out as our nearest major companion. It is the Andromeda Galaxy, and you can see it on a clear dark night with just your own eyes. It appears as a faint fuzzy smudge of light, but that smudge is the most distant object you will ever see without a telescope. That faint light has travelled for 2.5 million years to reach your eye. When that light began its journey, modern humans did not exist. Our distant ancestors were just beginning to walk upright on the African savanna. You are quite literally looking back in time to an ancient epoch. Andromeda is often called our sister galaxy, or twin. It is in many ways what the Milky Way would look like if we could see it from the outside. It is a magnificent spiral galaxy, a giant pinwheel of stars, gas and dust. It is actually larger than our Milky Way, perhaps containing 1 trillion stars compared to our estimated 400 billion. Like us, it has a bright central bulge of old stars, a massive disk with the spiral arms, and a supermassive black hole hiding at its very heart. It even has its own collection of smaller satellite galaxies orbiting it, just as we have the Magellanic Clouds. We in Andromeda, along with a few dozen smaller dwarf galaxies, make up our local galactic neighbourhood, fittingly called the Local Group. But this neighbourly relationship is not static. It is dynamic, and it is destined for a dramatic future. For nearly a century, we have known that the universe is expanding. Almost every galaxy we look at is rushing away from us, their light red-shifted, as the wave of light is stretched out by the expansion of space itself. But Andromeda is different. When we look at Andromeda, its light is blue-shifted. The light waves are compressed, not stretched. This means only one thing: it is not moving away. It is moving toward us: gravity. The great architect of the cosmos is pulling our two massive galaxies together. Andromeda is falling toward the Milky Way at a speed of over 250,000 miles per hour. This sets the stage for a cosmic event of unimaginable scale, a galactic collision. This is not a crash in the way we think of it. Galaxies are not solid. They are mostly empty space. If two cars collide, they are destroyed. But when two galaxies collide, the individual stars almost never hit each other. The space between stars is so vast that they will glide past one another like ghosts. The real collision is one of gravity. This grand event will not be an explosion, it will be a cosmic dance that unfolds over billions of years. The first pass is expected to happen in about 4 billion years. As the two galaxies swoop past each other, their immense gravity will grab and pull, the beautiful flat spiral disks will be torn apart. Long tidal tails of stars and gas will be flung out into intergalactic space, creating spectacular shimmering streamers hundreds of thousands of light years long. Our familiar constellations will be erased, the night sky completely rearranged. After this chaotic first pass, the two galaxies will fly apart, but they won't escape. Gravity will slow them down, stop them and pull them back together for a second, even more disruptive encounter. Over hundreds of millions more years, they will pass through each other again and again, like two boxers clinching. With each pass, their distinct structures will be destroyed. The gas clouds from both galaxies will slam into each other, triggering a starburst. A massive galaxy-wide firestorm of new star formation. The two supermassive black holes at their centres will begin a long spiralling dance, eventually merging into one even more massive black hole, releasing an incredible burst of energy as gravitational waves. When the dance is finally over, perhaps 6 billion years from now, the two beautiful spirals will be gone. In their place will be a new single enormous galaxy. It will no longer be a flat pinwheel. It will be a giant disorganized beehive of stars, a shape we call an elliptical galaxy. This new galaxy, sometimes nicknamed Milkomeda, will be one of the largest in our corner of the universe. And what about our solar system? Our sun will still be shining, though it will be an aging red giant by then. We will not be destroyed, we will simply be relocated. Computer simulations show we will likely be thrown by gravity into a new, much longer orbit, perhaps tens of thousands of light years from the new galactic core, surviving as silent witnesses to the birth of a new colossal island of stars. A zoo of galaxies. The leap that revealed Andromeda also revealed that the universe is a vast zoo filled with different species of galaxies. Just as Earth has different ecosystems, rainforests, deserts, oceans, the cosmos has different types of galactic ecosystems which we classify by their shape. 1. Spiral galaxies. The living cities. These are the classic galaxies, the pinwheels like our Milky Way and Andromeda. They are the most beautiful and for us the most familiar. They are living ecosystems because they are still actively building new stars. The anatomy. They have two main parts. In the middle is the central bulge, a bright, dense ball made mostly of very old yellowish-red stars. At the very centre of the bulge hides the supermassive black hole. The second part is the disk, a vast flat spinning plane of stars, gas and dust. The spiral arms. The most striking feature, the arms are not solid structures. You can think of them as cosmic traffic jams or density waves. The stars and gas clouds of the galaxy are all orbiting the centre, but they don't all move at the same speed. The spiral arms are regions where things get bunched up, the ecosystem. As gas clouds move into one of these arms, they get compressed by the traffic jam. This compression is the trigger for gravity to take over, causing the clouds to collapse and form hundreds or thousands of new stars. This is why the arms are so bright. They are filled with massive, hot, brilliant blue stars. These stars live fast and die young, so they never have time to drift out of the arm they were born in. Spirals are the fertile galaxies, the bustling cities of the cosmos. Variations. Some spirals have a straight bar of stars running through their centre, with the arms spinning off the ends. We call these barred spirals, and we believe our own Milky Way is one of them. 2. Elliptical galaxies. The retired empires. These are the old galaxies. They are the result of the cosmic dance of mergers, the future Milkomeda. The anatomy ellipticals have no disk and no spiral arms. They are just massive three-dimensional clouds or beehives of stars. They range in shape from nearly perfect spheres called E0 to long cigar-like shapes called E7. The inhabitants. They are filled almost entirely with old red stars. The stars don't orbit in a flat, organised disk. Instead, they swarm around the centre in random crisscrossing orbits like a swarm of bees. The ecosystem. Elliptical galaxies are retired or dead ecosystems. When their parent galaxies merged billions of years ago, all the gas and dust was either used up in one final giant starburst or blown out of the galaxy entirely. With no gas left, they can no longer make new stars. They are red and dead, simply growing older and dimmer, filled with ancient long-lived stars. They are often the largest galaxies in the universe, the empires that have grown by conquering and absorbing other galaxies. 3. Irregular galaxies, the chaotic workshops. These are the misfits of the galactic zoo. They have no defined shape at all. The anatomy. They are messy, chaotic and disorganized. They have no central bulge and no spiral arms. They look like a spilled cloud of stars and glowing gas. The ecosystem. Many irregulars are starburst galaxies. They are extremely rich in gas and are undergoing incredibly intense and violent bursts of star formation, creating new stars at a ferocious rate. They shine with the brilliant blue light of young hot stars. The origins. An irregular galaxy is often a system in distress. It might be a dwarf galaxy that is being bullied by a large neighbour. The gravity of the bigger galaxy pulls and rips at the smaller one, distorting its shape and triggering the starburst. Our own neighbours, the large and small Magellanic Clouds, are irregular galaxies that are being torn apart by the Milky Way's gravity. Other irregulars might just be very young galaxies that haven't had time to settle down into an organised spiral shape yet. They are the workshops or disaster zones of the cosmos. The cosmic web. When we zoom out from our local group past Andromeda, past the galactic zoo, we can ask one final giant question. Are all these galaxies scattered randomly through space? Is the archipelago just a random collection of islands? The answer is no, the universe has a structure. Imagine zooming out so far that our entire Milky Way is just a single speck of light. So far that the entire local group is just a tiny dot. So far that you can see billions of galaxies at once. When computer simulations and deep-ski surveys which painstakingly map the position of millions of galaxies revealed this map, they found something astonishing. The galaxies form a pattern, a vast, intricate, beautiful pattern that looks like a sponge or a network of neurons or the foam in a kitchen sink. This largest of all structures is called the cosmic web. This web is made of two main parts, the filaments. These are unimaginably long thread-like structures of galaxies that stretch for hundreds of millions of light-years across the universe. These are the highways of the cosmos. Galaxies are not scattered randomly. They are strung along these filaments like pearls on a string. These threads are the sponge part of the sponge, the voids. These are the opposite of the filaments. They are the holes in the sponge. The voids are colossal, nearly empty regions of space, vast oceans of darkness, hundreds of millions of light years wide. You can travel for an eon through a void and never encounter a single galaxy. Our own Milky Way and the local group are located on one of these filaments on the edge of a vast empty region called the local void. We are in the suburbs of a much larger city. Where the filaments of the cosmic web intersect, you get massive nodes. These are the superclusters, the great cosmic cities. These are huge pile-ups containing thousands of galaxies all orbiting each other in a chaotic swarm. But what created this web? Why isn't the universe smooth? The architect of the cosmic web is the most mysterious substance in existence, dark matter. This is an invisible stuff that makes up about 85% of all matter in the universe. We can't see it, we can't touch it, but it has gravity. In the very beginning, just after the Big Bang, the universe was almost perfectly smooth, but there were tiny microscopic clumps where matter was just a little bit denser. The powerful gravity of the invisible dark matter in these clumps began to pull in more matter. Over billions of years, this process sculpted the universe. Gravity pulled matter out of the less dense regions, hollowing them out to become the voids. It pulled matter into the denser regions, which collapsed into the long, stringy filaments. The dark matter formed an invisible scaffolding or skeleton, and thus normal matter we can see the gas that forms stars and galaxies simply fell into this scaffolding. The galaxies, therefore, are just the lights strung along the invisible skeleton of the cosmos. They are the luminous foam on the shore of a vast dark ocean. The cosmic web is the grandest structure we know, the ultimate map of our universe, showing that from the smallest star to the largest supercluster, everything is connected. As we drift through this cosmic ocean, looking at the shimmering islands we call galaxies, a profound thought begins to settle in. We've been admiring the light. We've been tracing the spiral arms, marvelling at the star nurseries, and feeling a sense of awe at the sheer scale of these structures. We've built our entire understanding of the cosmos on this light. The visible light our eyes see, the radio waves, the X-rays, everything that our telescopes can possibly detect. But what if I told you that all of it, everything we have ever seen, every star, every galaxy, every wisp of glowing gas in the entire observable universe, is just a tiny sliver of what's truly out there in the dark? It's a humbling, almost unsettling idea. But it is the conclusion that modern science has been forced to accept. All the matter we understand, the atoms that make up you and me and the planets and the stars, all of it accounts for less than 5% of the total stuff in the universe. We are in a very real sense living in a world where 95% of our reality is completely, totally hidden from us. The cosmos we see is just the foam on the surface of a truly fathomless ocean. And this ocean is shaped by two invisible forces that we are only just beginning to comprehend. We call them dark matter and dark energy. Let's start with the first part of this invisible architecture. We call it dark matter. We didn't find it by seeing it. We found it by noticing its shadow, by feeling its grip. The story of its discovery is a beautiful piece of cosmic detective work. It began when astronomers like Vera Rubin were carefully studying the way galaxies spin. Think of our own solar system. The planets closer to the Sun, like Mercury, move incredibly fast. The planets far away like Neptune move very, very slowly. This makes perfect sense. The Sun's gravity is strongest at the centre and gets weaker the farther out you go. We expected to see exactly the same thing in galaxies. We expected the stars near the bright, dense centre to be moving quickly and the very outer edges to be moving much more slowly. But when astronomers pointed their telescopes and measured the speed, they found something that seemed impossible. The stars on the very outer edges of the spiral arms were moving just as fast as the stars near the centre. This was a profound crisis. It was like watching a merry-go-round, where the horses on the outer rim are somehow keeping pace with the horses near the middle. The string of gravity from all the visible matter, all the stars and gas we could see, wasn't nearly strong enough to hold those fast-moving outer stars. They should have been flung out into the void billions of years ago. The galaxies should have torn themselves apart. Yet there they are, stable, beautiful, intact. This is the puzzle. The only way the galaxy can hold itself together is if it's filled with something else, something massive, something that has gravity but gives off no light. A vast invisible halo of stuff that surrounds the entire galaxy, holding it together like a giant unseen hand. This is dark matter. It's not dark in the sense of being black or shadowy. It's dark in the sense of being transparent. It doesn't interact with light at all. Light passes right through it. It doesn't interact with normal matter except through the gentle, persistent pull of gravity. There are almost certainly particles of dark matter streaming through your body, through this room and through the entire planet right now, and we feel nothing. You asked for an analogy like a figure skater. It's a perfect way to think about it. Imagine a skater spinning on the ice. When she pulls her arms in, she spins faster. When she extends them, she slows down. This is a fundamental law of physics. We expected to see this in galaxies, stars slowing down as they got farther from the center of the mass. But what we see is different. It's as if the skater is spinning with impossible speed even with her arms outstretched. It's as if her arms and her whole body were weighted with enormous invisible lead, providing a stability and a mass that we simply cannot see. The galaxy is spinning too fast for the skater we see, unless that skater is embedded in a much larger, heavier, invisible system. So what is this stuff? We still don't know. We know what it is not. It's not dust, it's not dead stars, it's not black holes. It must be some new exotic particle, something not included in our standard model of physics. And it's not just a small correction. For every 1 pound of visible matter, there are 5 pounds of this invisible dark matter. It is the invisible skeleton of the cosmos. It is the scaffolding you mentioned. When we run computer simulations of how the universe formed, we can't create galaxies at all unless we first add this scaffolding of dark matter. It was the dark matter that clumped together first under its own gravity, creating vast invisible structures. And then normal matter, the 5%, the stuff we are made of, was drawn by gravity into these pools of dark matter like water collecting in a valley. The galaxies we see are just the glowing light strung up on an enormous invisible frame. The web of dark matter is the true architecture of the universe, and we are just the decorations. And so the hunt is on. In the quietest places on Earth, deep underground in old mines, shielded from cosmic rays by a mile of solid rock, scientists have built detectors of almost perfect purity. They are giant vats of super-cooled liquid xenon or germanium crystals, waiting in perfect stillness, in perfect darkness, hoping to catch the faint infinitesimal clink of a single dark matter particle as it passes through and just barely nudges one of our atoms. It is one of the most profound and difficult experiments ever attempted. We are quite literally searching in the dark for the very thing that holds our universe together. But the scaffolding of dark matter, as mysterious as it is only about 27% of the invisible universe. The other even larger component, making up roughly 68% of everything, is perhaps the greatest mystery in all of science. We call it dark energy. If dark matter is the invisible pull holding things together, dark energy is the invisible push driving everything apart. The discovery of dark energy was a complete accident, and it shook cosmology to its very core. For decades we had a simple and fundamental question: what is the ultimate fate of the universe? We knew the universe was expanding thanks to Edwin Hubble. We knew that all the galaxies were moving away from each other, like raisins in a baking loaf of bread. The big question was, will this expansion continue forever? Or will the combined gravity of all the matter in the universe, both normal and dark, eventually act like a brake slowing the expansion down? We wondered if one day the expansion might stop and reverse, and pull everything back together in a big crunch. It was a cosmic tug of war, the outward momentum of the Big Bang versus the inward pull of gravity. In the late 1990s, 2 separate teams of astronomers set out to measure how much the universe was slowing down. They were trying to find the precise rate of the deceleration. To do this, they used a special kind of exploding star called a Type 1a supernova. These supernovae are wonderful because they all explode with almost exactly the same brightness. They are standard candles. If you see one that looks faint, you know it's far away. If it looks bright, you know it's close. The astronomers pointed their telescopes and found these exploding stars in very, very distant galaxies, and they measured their light. And what they found made no sense. The distant supernovae were fainter than they should have been. This meant they were farther away than all our models predicted. The only way they could be farther away is if the expansion of the universe hadn't been slowing down at all. In fact, it had been speeding up. This discovery was so profound, so world-changing, that it won the Nobel Prize. It's like, just as you described, throwing a ball up into the air. You throw it, you expect gravity to pull on it, you expect it to slow down, stop for a moment, and then fall back to your hand. Now, imagine you throw that ball, and instead of slowing down, it suddenly ignites a tiny invisible rocket engine. It shoots away from you faster and faster and faster, accelerating into the sky, disappearing from view. This is what we found. The universe is not just expanding, its expansion is accelerating. This is a complete shock. Gravity only pulls, it cannot push. Dark matter only pulls, it cannot push. So there must be a force, a pressure, a new energy in the universe that is repulsive. Something that is pushing the fabric of space itself apart. We don't know what it is, we have no idea. We simply gave it a name, dark energy. It's not matter. It's not light. It seems to be a property of space itself. It's as if every single cubic centimetre of empty vacuum contains a tiny but persistent outward push. It is a cosmological constant, an intrinsic energy woven into the very fabric of space-time. And because the universe is expanding more and more, space is being created every moment. And so more and more of this repulsive energy is appearing, making the universe expand even faster, which creates even more space and even more energy. It is the quiet, relentless, invisible push that is on the grandest scales winning the cosmic tug-of-war against gravity. So let us rest here for a moment in this new picture of the cosmos, a picture that is almost entirely invisible. Let's tally it up. The ordinary matter, the atoms that make the stars, the planets, the nebula, you and me, that is less than 5%. The invisible scaffolding, the dark matter holding galaxies together, that is about 27%. And the mysterious repulsive force, the dark energy pushing the universe apart at an accelerating rate, that is the rest, about 68%. 95% of our reality is a complete and total mystery. The universe is not only stranger than we imagine, it is stranger than we can imagine. This isn't a failure of science, it is its greatest invitation. It's a moment of profound humility. It is the universe looking back at us and reminding us that we have only just begun to open our eyes. Everything we've talked about, all the wonders of the cosmos, they are just the illuminated 5% shoreline of an ocean of ignorance. And as you settle in, as you let your mind drift, there is a strange comfort in this. It means the adventure is far from over. It means the greatest discoveries are still yet to come. It's a reminder that as you close your eyes, as you drift into stillness, you are part of a mystery so vast that it fills the entire universe. You are floating in an invisible architecture, held together by a force we cannot see and pushed gently apart by an energy we cannot comprehend. And in that not knowing, in that deep cosmic uncertainty, there is a profound peace, a quiet, cosmic stillness. If our journey through the stars has taught us anything, it is that the universe is a place of immense change. We see stars being born in fiery nurseries of gas, and we see them die in spectacular supernova explosions seeding the cosmos with the elements of life. We have looked deep into space and seen that entire galaxies, vast islands of stars like our own Milky Way, are in constant motion. But the most profound discovery of all was not just that they are moving, but that they are all almost without exception moving away from us. This discovery, made in the early 20th century, is the single most important clue we have about the origin of everything. The further a galaxy is from us, the faster it seems to be racing away. This is not because we are special or at the centre of some great exodus. This is happening because the very fabric of the universe, space itself, is expanding. A good way to picture this is to imagine a loaf of raisin bread rising in an oven. As the dough space expands, it carries all the raisins, galaxies along with it. If you were sitting on one raisin, you would look out and see every other raisin moving away from you. A raisin twice as far away would move away twice as fast, simply because there is more expanding dough between you and it. This is exactly what we observe in our cosmos. This realization opens a door to the most profound thought experiment in human history. If the universe is expanding today, it must mean that yesterday it was smaller. The day before that, it was smaller still. We can take this logic and run time backward, like rewinding a movie. The galaxies rush back toward each other, the vast distances between them shrinking. The further back in time we go, the smaller, denser and hotter the entire universe becomes. If we rewind the clock far enough all the way back, we reach a logical conclusion. There must have been a time when everything we see, all the matter, all the energy, all of our three-dimensional space and even time itself was compressed into an impossibly small, impossibly hot and impossibly dense state. This moment, this beginning of space and time is what we call the Big Bang. It's vital to clear up the biggest misconception about the Big Bang. The name itself is misleading. It suggests a bang, like a bomb exploding in the middle of a dark, empty room. This is completely wrong. The Big Bang was not an explosion in space, it was the expansion of space itself. There was no outside for it to explode into. There was no before, because time itself began at that moment. The Big Bang did not happen at a single point in the universe, it happened everywhere at the same time. The point that became your current location, the point that became the Andromeda Galaxy, and the point that became the most distant galaxy we can see were all at that first instant pressed together in that same extraordinary state. We cannot fully describe the very first instant. Our current laws of physics break down at such extreme energies and densities, but we can pick up the story a fraction of a second after the beginning. In these first fractions of a second, the universe was a seething, chaotic soup of energy and fundamental particles. It was hotter than the core of the most massive star measured in trillions of degrees. It was so hot that nothing we recognize could exist. Matter and energy flashed back and forth following rules we are still working to understand. The universe expanded and cooled with astonishing speed. When the universe was about 1 second old, it had cooled enough for the fundamental particles like quarks to bind together and form the more familiar building blocks of matter, protons and neutrons. For the next couple of minutes, the entire universe was a nuclear furnace. This period from about 1 second to 3 minutes after the Big Bang is called primordial nucleosynthesis. It is the universe's own creation event for the first elements. The universe was still incredibly hot and dense, acting like the core of a star but everywhere at once. Protons, which are the nucleus of a simple hydrogen atom, were everywhere. These protons could fuse with neutrons to form heavy hydrogen or deuterium. These deuterium nuclei could then fuse with other protons and neutrons to form helium. The universe frantically cooked these light elements, but this cosmic cooking show was on a strict timer. By the time the universe was about 3 minutes old, it had expanded and cooled so much that the fusion process stopped. The density and temperature dropped below the point where protons could overcome their repulsion and fuse together. The window of opportunity slammed shut. When it did, the universe was left with the ingredients it had managed to make: a huge amount of leftover hydrogen protons, a significant amount of helium, about 24% of the universe's total mass, and tiny traces of lithium. This prediction that the early universe should have created a mixture of roughly 75% hydrogen and 25% helium is one of the most powerful pieces of evidence for the Big Bang. When we look out at the oldest stars and most pristine gas clouds in the universe, this is exactly the ratio we find. We are seeing the universe's original recipe. After those first few frantic minutes, the universe entered what we could call its dark ages. It was still expanding and cooling, but it was a very strange place. It was completely dark, yet it was filled with a blindingly bright, hot light. This sounds like a contradiction, but it makes sense when you understand the conditions. The universe was filled with the newly formed nuclei of hydrogen and helium, but it was still too hot for them to capture their own electrons. The electrons zipped around freely unbound to any atoms. This created a fog. The universe was filled with a hot opaque plasma like the inside of the sun. Light particles, photons, could not travel freely. They would be created, move a tiny distance, and then immediately scatter off a free-roaming electron. The universe was a whiteout, a glowing, dense fog. No structures, no stars, no galaxies could form. This foggy period lasted for a very long time. The universe kept expanding, stretching the light and cooling down. Finally, after about 380,000 years, a critical milestone was reached. The universe cooled to a temperature of about 3,000 degrees Celsius, roughly the temperature of the surface of a red star. This temperature was the magic number. It was finally cool enough for the hydrogen and helium nuclei, with their positive charge, to capture the fast-moving negative electrons and hold on to them. This process is called recombination. For the first time, stable neutral atoms were formed. The effect of this was immediate and dramatic. The fog vanished. With the electrons now safely bound into atoms, the photons, the particles of light, were suddenly free. They were no longer scattering off electrons every instant. The universe, in a single grand moment, became transparent. The light that was unleashed at that moment, the first light to ever travel freely through the cosmos, has been traveling ever since. This is the oldest light we can possibly see. It is, in a very real sense, the afterglow of the Big Bang itself. We call this light the cosmic microwave background, or CMB. When it was first released, it was a hot, bright yellowish-white glow. But in the 13.8 billion years since the universe has continued to expand, stretching this ancient light. Just as the sound of a siren stretches to a lower pitch, as it moves away from you, the light from the Big Bang has been stretched to much longer wavelengths. What was once a visible glow at 3,000 degrees is now incredibly cold, measuring just 2.7 degrees above absolute zero. This light is no longer in the visible spectrum. It has been stretched all the way down into the microwave part of the spectrum. This is the echo of creation. It is not coming from one direction. It is coming from everywhere. No matter where you point a radio telescope, you will detect the same cold hiss left over from the dawn of time. When you tune an old analog television to a dead channel, a small percentage of that static is interference from the cosmic microwave background. You're literally seeing the leftover heat from the Big Bang. In the 1990s, satellites mapped this background radiation in incredible detail. They found it was almost perfectly uniform, but not quite. There were tiny microscopic variations in temperature fluctuations of 1 part in 100,000. These tiny hotter and colder spots were the seeds of everything we know. The slightly denser, colder spots had a tiny bit more gravity, and over billions of years they pulled in more and more matter. These were the seeds that grew into the first stars, the first galaxies, and eventually into us. This understanding of our past naturally leads to the ultimate question: what is our future? Knowing the universe is expanding, will it expand forever? Or will gravity eventually win, pulling everything back together in a big crunch? For decades, astronomers believed the answer depended on how much stuff was in the universe. If there was enough matter, its combined gravity would act like a brake, slowing the expansion down and eventually reversing it, leading to a fiery collapse. If there wasn't enough matter, the universe would expand forever, but at an ever-slowing rate. Then, in the late 1990s, came the biggest shock in the history of cosmology. 2 separate teams were measuring distant supernovae exploding stars to check how fast the expansion was slowing down. They found the exact opposite of what they expected. The expansion of the universe is not slowing down. It is accelerating. Something is pushing the universe apart faster and faster, overpowering the pull of gravity on the largest scales. We have no idea what this something is. It seems to be a property of empty space itself. We call it dark energy. This discovery fundamentally rewrote our understanding of the universe's ultimate fate. The most likely scenario is no longer a dramatic big crunch. Instead, it is a slow, cold, quiet end known as the Big Freeze or the heat death. The future this implies is staggering in its scale. As dark energy continues to accelerate the expansion, the galaxies we see in our night sky will be pushed further and further away. One by one, they will cross a cosmological horizon, a point of no return. They will be moving away from us so fast that their light can no longer reach us, even travelling at the speed of light. In 100 billion years, the night sky will be a very different place. Any observer in our Milky galaxy, the future merger of the Milky Way and Andromeda, will look out into the void and see nothing. Every other galaxy in the universe will have receded beyond our view. The sky will be dark, empty and isolated. Inside this one lonely supergalaxy, the process of entropy will continue. Stars are nuclear furnaces and they cannot burn forever. The vast reserves of gas used to form new stars will eventually run out. The era of star birth will end. One by one, the stars that light the galaxy will die. The massive stars will have already exploded. The medium-sized stars like our Sun will puff off their outer layers and become cold dead white dwarfs. The smallest, longest-lived red dwarf stars will finally gutter out after trillions of years, becoming black dwarfs. The universe will become a graveyard of cold, dark stellar remnants, black holes, neutron stars, and dead chunks of rock. It will grow ever colder, approaching absolute zero. Even these remnants may not be permanent. Over truly unimaginable timescales, black holes themselves may evaporate through a process called Hawking radiation. The universe will become a vast, dark, cold, and silent expanse filled only with stray weakening particles of light and energy infinitely far apart from each other. This is the Big Freeze. It is not a dramatic end, but a slow quiet fading into an eternal unchanging night. The grand story of the cosmos, which began in such an incomprehensibly hot and energetic instant, will dissolve into a cold, empty and silent equilibrium. And so as we float in this vast, quiet darkness, having looked at the birth and death of stars and the grand architecture of the galaxies, our minds eventually come back to a tiny, personal and perhaps the most profound question of all. We look up from our small blue world and we whisper it into the void. Are we alone? Is this complex, beautiful, fragile thing we call life? Is it just a fleeting accident, a lucky alignment of molecules on a single speck of dust orbiting an average star? Or is the universe teeming with it? Is the cosmos a garden and we are just one flower that has just opened its eyes? For almost all of the human history, this question was pure philosophy. It was a dream for poets and a speculation for thinkers. We had no mayor. We only knew of our own solar system. We had Earth, a vibrant oasis. And then we had barren rocks like Mercury and Mars and giant cold storms like Jupiter. It looked empty, but our sun is just one star. One. one of perhaps 400 billion stars in our own Milky Way galaxy. And our galaxy is one of hundreds of billions, maybe trillions in the observable universe. The numbers are so large they become meaningless. They are just static. But in the last few decades, everything has changed. The question has moved from philosophy to science, because we finally developed the tools to look, not with our eyes, but with instruments of incredible sensitivity. We started to look for planets, not in our solar system, but orbiting other stars. We call them exoplanets, and we didn't just find one or two, we found thousands. As of today, we have confirmed over 5,000 worlds orbiting other suns, and that's just from the tiny, tiny patch of sky we've been able to look at closely. The real number just in our galaxy is estimated to be in the billions. Perhaps there are more planets in the Milky Way than there are stars. Suddenly, the universe doesn't look so empty anymore. Suddenly, the galaxy is revealed to be a place of endless hidden worlds. But how? How do you see something as small as a planet when it's light years away and completely overshadowed by the blaze of its parent star? It's like trying to spot a firefly sitting next to a searchlight from 100 miles away. We had to be clever. We don't see the planet itself. Instead, we watch for the tiny, subtle ways the planet affects its star. One of the main ways we find them is called the transit method. Think of it like this. Imagine you are looking at a single bright street lamp far down a long, dark road. It's just a steady, constant point of light. Now imagine a tiny gnat flies exactly between you and the bulb. For just a fraction of a second, the light would dim, a tiny, almost imperceptible wink. You wouldn't see the gnat, it's too small and it's not lit, but you would know something had passed in front of the light. This is what our telescopes, like the Kepler Space Telescope, were designed to do. They are giant sensitive light meters. They stare and stare at a patch of hundreds of thousands of stars all at once for years. They just measure the brightness, and they wait for a star to wink. They wait for that tiny rhythmic dip in brightness that happens when a planet in its orbit passes directly in front of its star from our point of view. If the dip is very small, we know the planet is small, perhaps the size of Earth. If the dip is large, we know it's a giant like Jupiter. And if the dip repeats, if it happens every 10 days, we know the planet has a 10-day year. If it happens every 300 days, we know it has a 300-day year. It is an act of incredible cosmic patience, just watching the stars blink. And from those tiny blinks, we have mapped worlds. But what if the planet's orbit doesn't cross in front of its star from our angle? We have another way. This one is even more subtle. It's called the radial velocity method. We often say a planet orbits a star, but that's not quite the whole truth. A planet and its star both orbit their shared center of gravity. Imagine a large, strong athlete holding hands with a small child and spinning them around. The child swings way out in a big circle, but the athlete doesn't stay perfectly still. To balance the child's weight, the athlete has to lean back and they wobble in a small circle themselves. A big planet, even one we can't see, does the same thing to its star. As the planet swings around, it tugs on the star with its gravity. It makes the star perform a tiny, gentle wobble. We can't see this wobble, but we can measure it. We can measure it using the color of the star's light. As the star wobbles toward us, its light waves get compressed and the light shifts just a tiny bit toward the blue end of the spectrum. As it wobbles away from us, its light waves get stretched, and it shifts just a tiny bit toward the red. This is the Doppler effect. It's the same reason an ambulance siren sounds high-pitched as it races toward you and low-pitched as it races away. By measuring this incredibly small rhythmic shift in the star's color, from blue to red and back again, we can detect the gravitational pull of an invisible world. We can feel its presence weighed by gravity itself. And so using these methods and others, the catalogue of worlds has exploded. We have found hot Jupiter's gas giants orbiting so close to their stars that their years are only a few days long. We have found super-Earth's rocky planets larger than our own. We have found planets orbiting two stars at once, worlds with two sunsets like something from a science fiction film. But our search isn't just for any planet. We are looking for something very specific. We are looking for a place like home. This brings us to one of the most beautiful and hopeful concepts in astronomy, the habitable zone. You might know it as the Goldilocks zone. It's based on a simple fairy tale. Goldilocks didn't want her porridge too hot. She didn't want it too cold. She needed it to be just right. A planet to support life as we know it needs the same thing. If a planet orbits too close to its star, it's baked by radiation. The heat is so intense that any water would instantly boil away, becoming a thick, crushing steam in the atmosphere. a runaway greenhouse effect. Think of Venus, a toxic, scorching hothouse, too hot. If a planet orbits too far from its star, it is lost in the freezing dark. The star is just a distant, bright pinprick. Any water would be frozen solid, locked into a world of ice hard as concrete. Think of Mars or the moons of Jupiter. Too cold, but in between, in every solar system, there is a just right orbit, a perfect temperate ring around the star, a distance where the energy received is exactly right, not to boil water and not to freeze it, but to let it exist as a liquid. Oceans, lakes, rivers, rain. Here on Earth, wherever we find liquid water, whether it's in a boiling volcanic vent at the bottom of the ocean or in a pocket of brine in the Antarctic ice, we find life. Liquid water is the solvent. It's the medium where the complex chemistry of biology can happen. It is the cradle. So the first thing we do when we find a new rocky planet is we ask, where is it? Is it in the just right zone? And we have found many. One of the most astonishing discoveries is a system called TRAPPIST-1. It's about 40 light years away. In galactic terms, that's our next door neighbour. The star itself is tiny. It's an ultra-cool red dwarf star. It's not a bright yellow sun like ours. It's a dim, smouldering reddish ember. It's barely larger than the planet Jupiter. But orbiting this dim, cool star, we found 7 planets. 7 rocky Earth-sized worlds. And because their star is so cool, their just right habitable zone is huddled very, very close to the star. All 7 planets are orbiting closer to their star than Mercury orbits our Sun. They are a tiny, compact family of worlds. If you were standing on the surface of one of them, the other planets in the system wouldn't look like stars in the sky. They would look like moons. Huge visible worlds hanging in the dim red light. The sky would be a permanent salmon-coloured twilight. And of these 7 Earth-sized worlds, at least 3 and maybe 4 are orbiting in the habitable zone. 3 worlds all about the size of Earth, all with the potential for liquid water on their surfaces. Imagine that, a whole solar system full of candidates. We don't know if they have water. We don't know if they have atmospheres. Not yet. But they tell us something vital. They tell us that worlds like ours are not a mistake. They are not a 1 in a trillion miracle. The universe, it seems, is built to make them. And so our long journey through the cosmos finally circles back, returning to where it always must to you. We have travelled across vast, unimaginable distances in our minds, across billions of years and past countless galaxies. But the most profound discovery, the most important truth, isn't found in the farthest reaches of space. It is found right here in the quiet of this moment, in the very fact that you are here to listen. There is a simple, beautiful and literal truth that connects us to everything we have seen. We are made of star stuff. This is not just a poetic idea, it is a physical reality. The universe is not just out there, a distant spectacle we observe. It is in here. It is inside us. Think about the atoms that make up your body. The carbon that forms the foundation of your cells, the oxygen you are breathing in right now, the calcium in your bones and the iron in your blood. These materials were not made on Earth. They were born in the heart of a star. Long ago, in the early universe, there were only the lightest elements, mostly hydrogen and helium. Life needs heavier things like carbon and oxygen. These were built inside the fiery cores of giant stars. For billions of years, these stars acted as cosmic factories, fusing simple atoms into the complex materials required for life. But how did those materials get from a distant star into your body? The stars in their final moments gave them to us. When massive stars end their lives, they explode in a glorious blaze of supernova. This explosion scatters all those precious life-giving elements, the carbon, the nitrogen, the iron across the galaxy. This stardust then drifted through space for eons, gathering into new clouds. Our Sun, our Earth, and our entire solar system were formed from one such cloud of recycled star material. That dust became our planet. And over billions of years, that same dust learned to organize itself. It became the oceans, it became the first simple life, and eventually, after a very long journey, it became you. When you look at your hand, you are looking at atoms that were forged in a star. When you feel a connection to the night sky, it is the cosmos recognizing itself. You are not separate from the universe, you are the universe. You are the universe's way of thinking, feeling, and wondering. So as you close your eyes and prepare for sleep, let this thought bring you a deep and gentle peace. You're not small or alone in the vastness. You're a part of this grand cosmic story. You're as ancient as the stars and as connected as the light that travels between them. Let your mind drift. Feel the rhythm of your breath, a rhythm that connects you to the tides of the ocean and the spinning of our world. You are a piece of starlight, a dream of the cosmos. Good night. May your rest be peaceful as you float gently on the same quiet cosmic currents that flow through us all.